Starting in on Course Pack 515, talking about unpressurized tanks and how the pressure translates into stresses in the walls in cases like this. Unpressurized tanks, fish tanks, or such structures used for liquid storage, and these structures can undergo significant hoop stresses towards the bottom of the structure. From the fluid mechanics of it, the pressure due to the weight of the fluid varies with increasing depth. And one way to think about that, if we think of a volume at the bottom of the tank that has a cross-section of A, the little cube that we're considering has a volume that is the area times the depth, or rather the fluid column above our chosen area is a volume that is the depth times the area, and the weight of that acting on our chosen area surface is that area times the specific weight. Well, pressure is the amount of force distributed over an area. So if we simply rearrange this, it is a pressure. It's the weight of the water distributed over this control area. So pressure is this specific weight, and because pressure is this hydrostatic, the pressure on the wall, because of that same column of water, is the same. So we have a hoop stress developed in the wall of the tank that is the amount of pressure times the radius over the thickness of the wall. Now, we have no pressure in the tank in this case, so there's no axial stress. The hoop stress is around the tank in this direction, and you would have axial stress in this direction if this were capped and pressurized. Being that it's open, there is no axial stress. If you then instead put a lid on your tank, that would then become a plain axial P over A load. So those are considerations, thinking about if your tank has a lid and whether or not you're going to develop sufficient hoop stresses towards the bottom of the structure that would be a significant design constraint. So that's how to deal with open-topped tanks. All semester, we've primarily dealt with things that were much larger in one dimension than the other: our beams, bars, rods, shafts, etc. We then recently considered plates or shells, where we have things that are essentially two-dimensional, like a piece of paper has length and width and sort of this insignificant thickness, or things that don't change across the thickness. And the next couple of pages investigate what happens when there is variation in the thickness of this pressure vessel, the thick-walled pressure vessel. So one of the things that you might commonly run into that has to be treated as thick-walled is a hydraulic cylinder. Just like our IKEA shelf, where the stresses in our bookshelf were far below or gave a very high factor of safety against actual yield of the material, the deflection was a consideration. in the same way, this hydraulic cylinder has to have very minimal deflection so that the hydraulic fluid that's doing the work stays inside the cylinder. So, this is the first and only case in this class where we are actually going to consider a three-dimensional stress state. We are going to have the hoop and axial stress, like we've dealt with before, but now we're also going to consider this radial stress that happens in the thickness direction. The equations that deal with this consider the inner radius of the structure, r sub I, the outer radius of the structure, we have a sigma sub r is our radial, sigma sub h is our hoop, and sigma sub a is our axial, and P is the amount of pressure inside the structure. So in this case, we are going to consider a hydraulic cylinder that has a 2-inch inner diameter. So if we look at this in cross-section, we have 2 inches across this way and a 1/2-inch wall thickness. So therefore, my R sub I is 1 inch, and if it's a 1/2-inch wall, then my R sub 0 is 1.5 inches. R sub I is 1 inch. R sub O, outer radius is 1.5. Okay, we've got an internal pressure of 5,000 psi. So